Hello everyone. So here we have another problem. So this in this video, this is like a part two of the video. So if you're coming directly here, look at part one on symmetrical fault analysis. This is part two of the video, and we had seen how to what kind of faults are there, how to do fault analysis and all. And this is like a continuation, and I'm taking up this problem here. So also assumptions. So no load at the beginning. So we had solved a problem in part one with load and without load. So both cases we have considered. But here I would like to do no load case because it is easy, it is simpler to do it. And then all voltages are 1 per unit. So Vi equal to 1 where I equal to 1, 2, 3. So under these assumptions, determine the fault current if a three-phase bolted fault occurs at bus 3, bus 2 and bus 1. So I have these three cases and this is my simple power system. Two generators are there. It is not given how much is the MVA rating and all, but that's not required because already all the impedances, everything are marked in either percentages or in per units. And for the generators, the subtransient reactance is already given, so that is already useful for calculating fault currents and all. So let's begin the solution. You already know how to do this based on your experience of seeing the previous video. So you may pause the video right now and you can attempt the solution, and later on you can also match with what I have done. So the approach that I am going to take now is, first is I will build the Z bus. Okay, so why do I want to build the Z bus? So we want to build the Z bus because uh, the fault anyway we have to do for all the three buses. So therefore having a Z bus will be useful. And we need to find the Thevenin's impedance of 1, 2 and 3 as a part of the fault analysis. So you will also see how calculating Z bus will help in knowing the Thevenin's impedance. So in any ways, let's get started by finding out the Z bus. So we had studied some formulas before about how to build the Z bus, and we had. So let's try to implement what you have learned and try to build the Z bus for this. So step one. So again, this is the proof that, or this is a just to show that the how the Y bus is useful for load flow studies. Similarly, the Z bus is useful for fault analysis. Okay, step one, I have this 8% or J 0.08 connecting to bus 1. So this is my first step. So what will be my Z bus? The first step, that is nothing but J 0.08. So this I am adding to. So from reference I am adding to bus 1. Now for bus 1, I'll again connect a line to bus 2. So that will be my step 2. So J 0.1 added between 1 and 2. So because 2 is a new bus, so I'll just write it here. The size of the system will increase J 0.08, and I'll have to, because I'm adding to bus 2, I'll have to copy this here J 0.08, and this I have to copy it here J 0.08, and then here I will have to add. So I will have to add this Z11 with the Z base. So this is 12%, this is 8%, total will be 20%. So I'll just add here. I'm sorry, not this 12%, this one. So this is 10%, 8%. So 0.18 will be my Z22 element. So this is my Z bus after adding these two elements. Now in the next step, I can add the third element, or I can add this one. So I have two choices. So let me take up this one. So adding 0, this is 0.12. So I'll write like this. Step 3, adding J 0.12 between bus 2 and reference bus. So if you notice, this is a case where we are this is case 3, I suppose. So in one of the in the earlier we had these cases. So this is the case 3. So how to find the Z bus in third step? So we'll have to apply the Cron's reduction. So you take the old Z bus. To that old Z bus, I have to subtract 1 by Z22 plus ZLL. Sorry, Z 0.12. So this is 18 18 plus J 0.12, and here I have to multiply the second column, and I have to multiply it with the second row. I think this is 18, sorry. So this is also 18, 0.08, and then J 0.18. So I believe this is the formula for doing that. So I think let me quickly verify it. I'll just open. So this was our earlier lecture notes, and this was the set of formulas. So I think this is the case we are talking about. New line added between the reference and existing bus. So you take the bus and then minus 1 by zkk column, and okay. So I think I have got it correct. So let me go to my present page now. So this is all correct. So I'll just use this to do it. So create a new file. So Z old is equal to I into 0.08, 0.08, second row 0.08, 0.18. So this is my old Z bus. So if I execute it, so I'm getting here first column and second column, so that is fine. So K equal to 2, and then ZB equal to 0.12 per unit. So this is I into 0.12, and then ZKK will be, okay, we can directly do that. So Z new will be nothing but Z old minus 1 divided by ZB plus ZKK. So that is Z old K comma K. So this will be multiplied. So I'm just doing a 2-line equation. This will be multiplied by the column matrix. So Z old, all rows, second column, multiplied by Z old, second row, and then all columns. So this is what will be my new Z bus. So I'm getting some values. So let me also just quickly verify. Okay, I'm getting the second column properly, and then 2 comma 2, and then all right. So looks like I have not made any mistake. So this is my final solution, 0.05867. I'll anyway do double check. So 0.058 0.67. I'll leave it there. And 0.032J, and then J 0.032, and this one is J 0.072. So this is my Z bus after adding, after third step. Now finally I have the fourth step where I am adding a J.1 to the second column. So this is again case 2, I suppose. So ZB4 will be, to second column I am adding 0.1. So I'll keep the first row as it is. Then this also I'll just keep as it is. Now to this I'll copy it here, J 0.032, J 0.072, and this row I'll copy it here, the second row. Then to this I'll add the 0.1, so I'll get 172. So hopefully this is my Z bus for the system. So let's do quick verification just to be sure, double check. First I will form the Y bus and then invert it. So this is what we are most familiar with. So how to form Y bus? Between 1 and 2 minus J10. So that will be J10. Between 1 and 3 nothing. So this I will copy it here. Between 2 and 3 also minus J10. So it will be J10 here. And then J10 here. Now what is 1 by J 0.08? That will be minus J 12.5 and 1 by J 12. So this I will have to check. 1 divided by 12. So 8.33. So J 0. J. So not 12 actually, 0.12. So 8.33 with a minus sign. So these are the shunt impedances here. So which will be added to the first one. So this will be minus J 22.5 and this will be minus J 18.33. So minus J 22.5 minus J 18.33 and this will be minus J 10. So now if I invert this, I should get the Z bus. So let's quickly verify. So let me form Y bus. So this will be I into minus 22.5, 10 and 0. Second row 10 minus 18.33, again 10. Oh, there is one more 10 here. So this will be 28.33. So here I'll keep 28.33. So 10 and 10 are coming from the branches and then 8.33 is coming from the shunt element. Alright, so 0, this will be 10 and finally it will be minus 10. So simply I'll take the inverse. So let's see. Somewhere there's an error. Line 4. Oh, here. Right. Alright, so I got this finally this thing. So luckily I think everything seems correct. So I just want to print the imaginary part of Z bus. And then if I run this, IMAG. So this is the Z bus after inverting the Y bus. So let me just paste it here. So Z bus is nothing but J into this. So I think the answer is exactly matching 0.58, 0.32, 0.32. Okay, so this is such a relief that what we have done is correct. So this is the bus impedance matrix of the system. Alright, so we have done one step. So the question given was to find the fault currents, and what we ended up with is calculating the Z bus and then verifying with inverting of Y bus. So everything is good now. Now what I'll do is just forget about this for a moment, and then let's find Thevenin's impedance. Thevenin's equivalent impedance. So first thing you should notice, if I go back, it is mentioned that system is on no load and all voltages are equal and all angles are also equal. So therefore, all currents are also zero. So only current that will flow will be because of the Thevenin's voltage that we are introducing either at bus 3, at bus 2 or at bus 1. Now imagine we are at bus 3 and I short circuit the other two. I want to find the equivalent impedance. So what will be my so ZTH with respect to bus 3. So for that, I'll make a small circuit like this. So this is your bus 3. Looking from bus 3, so what are the impedances? This is 12%, this is 8%, this is 10% or 0.1, and this is also 10%. So what is the impedance? So these two are in series and that is in parallel with this, and then overall is in series with this. So ZTH is nothing but, first these two are in series. So J 0.08 plus 0.1. This element is in parallel with J 0.12 and the whole thing is again in series with J 0.1. So how do we solve it? J 0.18 parallel with J 0.12. Alright, this is in series with J 0.1. Now what is the parallel combination of these two? 0.18 into 0.12 divided by 0.18 plus 0.12, and j can be taken common because in the numerator there will be j square, in the denominator there will be j, so j square and j, one of the j will cancel, so I'll get j like this, and then this is the calculation. So 0.18 plus 0.12, I'm sorry, this is multiple, okay, I can use this, 0.18 multiplied by 0.12, this whole thing is divided by this. So 0.072. So I'm getting 0.072J plus J 0.1. So finally this is J 0.172. So this is the Thevenin's. So this is Z Thevenin for bus 3. Now if I go back and check here, you see this number is nothing but Z33. So instead of finding the Thevenin's equivalent, I can actually find the Z bus, and then this Z33 is nothing but Z Thevenin for bus 3. So will the Z Thevenin for bus 2 will be this one? So that creates a doubt. And will the Z Thevenin for bus 1 will be this one? So let's calculate that again. So let's again give it a pause. Find out what is the Z Thevenin for bus 2. So let me get the system once again. So I'm just drawing it from my memory. This is 0.08 and this is 0.1, and then bus 2, this is J 0.12, and then this side J 0.1, and then this side is open circuited. See, at bus 3 there is no load connected. So now I am interested in, if I take these two as AB terminals, I am interested in impedance between the points A and B for the system. So, so it is nothing but Z Thevenin for bus 2 is nothing but, I'll just simply have to do this. So J 0.18 in parallel with J 0.12. This we already know. Just now we calculated this one. And this element, if I go up again, so this is exactly matching with what we have here. In fact, here what we have, it is exactly matching with that. So Z22 element is, this is nothing but Z22. So you notice that this exercise is not required. So when this question was asked, so suppose I'm writing the exam and this question is asked, so I know all three buses are covered. So I'll first find out the Z bus, and then directly I'll go to calculation of fault currents. This is just only for your conceptual understanding, I'm telling. So let's find out the Thevenin's impedance at bus 1. So how to find Thevenin's impedance at bus 1? So this is the bus 1. So this one is the bus 1. So I take this point and this point, J 0.08, and then I have J 0.1, then J 0.1, then I have J 0.12, and then finally I have this. So A, B are the points. This side is anyway no load, so it is open. So since this branch is open, this can be simply ignored. Then this branch total will be 0.1 plus 0.12. It will be J 0.22, 0.22 in parallel with J 0.08. So Z Thevenin for bus 1 will be J 0.08 into J 0.22 divided by J 0.08 plus J 0.22. So that will be how much? J 0.3. So this is our calculation. So this is 0.08 multiplied by 0.22 divided by 0.3. So I'm getting 0.5867. J 0.5, I'm sorry, 0.5867 per unit. And then if I again go up and check with my Z bus, so exactly it is matching with this 0.5867. It is matching. So therefore I have this question. So now calculation of fault current. Since the existing, since like in the, it is assumed that the system is no load and all currents are zero, so I don't have to perform any superposition kind of analysis. It's just like I only consider the voltage at the faulted bus, and then I just find out the this thing. And also the bolted fault it is said, so it's even more easier now. So there is nothing to do. So bolted fault means just fault impedance is zero. So I just get this. So I'll show you what I mean. So calculation of fault current. So at bus 3, if the fault is at bus 3, then simply I have a system like this. This is Z33, and then I have the fault. So 1 per unit, and then I don't have any this one. So fault current will be like this. So IF will be 1.0 divided by Z33. With the same logic, so at bus 2, IF will be 1.0 Z22. And with the same logic, at bus 1, the fault current will be 1.0 by Z11. So like this. So therefore, if I have, So let me store this in a variable. So I'm just storing this in a capital Z. So I'm just storing the magnitudes. So therefore 1 comma 1 will be like this. So 1 divided by this one. So this 17 per unit is the fault current. So the fault current will be minus J 17.044 per unit. Fault current at bus 2 will be, so if I just simply change it to 2, 13.866, and similarly fault current from Z33 5.81. So one thing you notice, as we move away from the generators, the fault current is reducing, and closer to the generator, fault current is higher. So that is another observation that we can do. We can actually find the fault current in amperes using this. So, but I'll not do that in this problem. But hopefully you learned something by solving this problem. So I have given a simple unloaded system and demonstrated how, first of all, this is just a review of how to build a Z bus, and then how to verify whether your Z bus is correct or not, and then the the elements of the Z bus diagonal are nothing but the Thevenin's impedances at each bus. So we can use that information to do the fault calculations. So I hope now you understood something about how to solve fault currents for a given system. So, with this, I'll conclude the topic of symmetrical fault analysis, and we'll see what will be the next topic. Thank you.